At the end of the last slide set, we were talking about how solar energy input varies with latitude, as it says at the top of this slide. We get more and more concentrated energy coming in at the equator for a variety of reasons, and then we get less energy being delivered to the polar regions. This results in a movement of energy from the equatorial regions to the polar regions, and this energy movement happens in the atmosphere through what we call convection currents. We're also going to see later that ocean currents will help move this as well, but we're focused on the atmosphere right now. So we get these convection currents. The model on the right is kind of a simple model showing how that convection current would work, all things being equal. However, there are a few complexities that result in us not having this super simple version. There's a slightly more complicated version. So the first complication is what we call the Coriolis effect. It's going to influence the movement of air and atmospheric circulation. What happens, pretty simply put, is that the air that's trying to go from the equator toward the poles is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. And likewise, the air that's trying to return from the poles to the equator is going to be deflected to the right in the northern hemisphere and the left in the southern hemisphere. The end result of all this is that global air circulation actually sets up like this. The air that is headed from the equator to the poles is essentially going sideways by the time it gets to about 30 degrees north and south latitude, and so it sinks and then heads back to the equator. Some of it, however, continues its journey. It continues to head north, but by the time it gets to about 60 degrees north or south latitude, again, it is going sideways, and in this case, it rises, and then it finishes its journey. It's got 30 more degrees of latitude to go. It gets to the poles where it sinks back down. Now, if you remember from some previous images that we had, and let's take a look at this from the side, this is how the circulation pattern goes. But you'll also remember we said when air rises, it cools and becomes less dense. It is less able to hold its moisture. And so in the middle here at the equator, we have a very cloudy area. It's called the intertropical convergence zone. It is very rainy there. And what's going on is the moist air is rising. If you're right there at the equator, you encounter something called the doldrums, which is there's not a whole lot of surface winds blowing at the ITCZ because the air is actually going up. It rises, we get rain, and so we get a very rainy climate when we're near the equator, or more specifically when we're at the ITCZ. So you want to remember this meteorological equator, which roughly coincides with the Earth's equator, and we'll see why it doesn't exactly in a little bit. Now, the air coming toward the convergence zone forms what we call the trade winds. These are pretty consistent surface winds that blow from northeast to southwest if you're in the northern hemisphere. If you're in the southern hemisphere, they blow from southeast to northwest. So they're basically blowing toward the equator and a little bit toward the west. And because they're blowing a little toward the west, they will tend to push ships along the trade wind pattern from east to west. So when Columbus came to North America, for example, the reason he came across where he did was he was taking advantage of the trade winds. So if you go north or south from the equator, when you get to about 30 degrees north and south, remember this is where the air is sinking. You'll notice it says subtropical jet here in the upper atmosphere, but you'll notice that the air is sinking down. When the air sinks, it warms and it absorbs moisture. And so these areas, 30 degrees north and south roughly of the equator, are places where we have some very large, significant deserts. And the Sahara Desert is the one with that probably most people are familiar with. That's at around roughly 30 degrees north of the equator. We continue to what's called the westerlies. So once you get up in this zone right here, between what's called the subtropical high and the polar front, you'll notice that the air is blowing toward the poles on both sides. These winds, because of the Coriolis effect, are deflected toward the east. And so this forms what are called the westerly winds, because the wind is blowing from the west, generally toward the east. This is where we live. So our predominant wind direction is usually from the southwest toward the northeast. That's our dominant wind direction. And most of our storm systems come in from the west. So, and that's because this is where we live. We live under the influence of the westerlies. Next up is where this air rises, is called the polar front. It's at roughly 60 degrees north and south. You'll notice they have another band of clouds here because as air rises, it expands and cools. Water droplets form in clouds. It gives up its water, and so you get a rainier or wetter climate. And that's the influence that we also live under. We will see in a little bit that our weather systems tend to be weather systems associated with the polar front. And then to complete our journey, we go to the polar high, which is where the air sinks down at the north and south poles. And this should tell you that because the air is sinking, air that is sinking warms, although at the poles that's a relative term, but it warms and it absorbs moisture. And so at the north and south pole, we actually have what we would consider to be desert climates. The air is quite dry there. Even though the south pole in Antarctica is covered with ice, the amount of snow that it gets in a given year, if you converted that to water, you would see that it's actually a desert type climate. So that sets up our global air circulation patterns. We have another bit of complexity to add, and that is seasonality. So if we look at the position of the planet compared to the sun, what we'll see is that where the sun's rays hit directly changes over the course of the year. So in what we would call the summer for the northern hemisphere, that is when the northern hemisphere is pointed more toward the sun and we're getting more direct light from the sun. What's especially notable and noticeable is that the meteorological equator, you'll notice the ITCZ would now be here. It would get as far north as about 23 degrees north latitude, which is what we call the Tropic of, I think, Capricorn. In our winter, things are just the opposite. So this peaks at December 21st. The sun is pointing directly at 23 degrees south latitude. That's roughly where the meteorological equator will be. And so all of the zones that we looked at on this slide will move north in our summer and south in our winter, which means that for our weather, this polar front will move south closer to our area in the winter, and it will move north away from our area in the summer. That also means that this subtropical high will move north in our summer and it'll get closer to us. So that's when we get those hot, dry days in August. And then in the winter, of course, it moves back south and things get wetter during our winter and spring. So what kind of patterns do we get out of this? Well, the monsoonal patterns are the really noticeable ones associated with the shifting north and south of the intertropical convergence zone, and we'll see that in a couple of slides. Some coastal areas get to experience what are called land and sea breezes. We'll take a look at that. And then we'll finish up by taking a look at cyclones, which are huge rotating low pressure air masses. They are not tornadoes. A cyclonic system is just a large weather system. And I should point out the ones that we experience are the extratropical cyclones. They form at the polar front. Occasionally a tropical cyclone, which if it's really strong would be called a hurricane. Occasionally tropical cyclones will reach our area. So let's take a look at these one by one. The first one to take note of is what we would refer to as a monsoonal climate, which probably should be on this slide deck, but you can see monsoon is listed here. And the big one down at the bottom shows where the intertropical convergence zone goes in July. And in January, it's along that blue line. And remember, that is where the air is converging, and so there's going to be rain underneath that line. You'll notice the line doesn't stay in the same place. So if you look at the two smaller maps on the upper right, you'll notice that as the ITCZ moves, the places that get that rain will change. And this seasonal change in rain, and the rain can be quite heavy, this seasonal change in rain is what we refer to as a monsoonal climate. And it's related to this tilting of the sun moving the intertropical convergence zone, which you see here in the middle, north and south over the course of the year. So let's take a look at sea breezes and land breezes. If you ever go to the coast, this is something that most people notice. If you go to the beach, especially by midday and afternoon, you'll see a pretty strong onshore flow of wind. And the reason for that is in the upper right-hand corner. Remember, the sun warms the land and the land warms the air. Let's take a look at this picture right here. That's this part right here. The sun warms the land and water, and then that warms up the air. Well, warm air rises. And so as the warm air rises, it pulls in cool air from over the water. And remember, water has a very high heat capacity, and it can absorb a lot of energy before it changes temperature significantly. Land has a low heat capacity, so it's going to heat up much more quickly when the sun shines on it. And because it heats up more quickly, that's why we have the warmer air over land during the day. That warm air rises, you get clouds and rain. But it also means if you're at the beach, it stays relatively clear, and you get a nice cool breeze coming off of the ocean. At night, the opposite happens. The land gives up its heat more quickly, and the temperature drops faster. The water hangs on to that energy, and so now you have warmer air over the water, and this kind of warm, humid air that formed over the land during the day and during the rainstorms that happen in the afternoon now move offshore, and so you get kind of this sticky, warm breeze coming off of the land that actually makes the beach a kind of unpleasant by the time you get to later in the night. This effect is doubled over Florida because you have a body of water on either side. You've got the Gulf of Mexico on the west, the Atlantic Ocean on the east. That rising air and the onshore flow converge over Central Florida, and Central Florida has pretty regular occurrences of thunderstorms almost every day in the early to mid-afternoon as this kind of reaches its peak. So what we'll do on the next set of slides is we'll talk about extratropical and tropical cyclones and a little bit about global warming.